I'll just wait a couple of more minutes to see if some more people show up. Okay, so we are going to be finishing up the material today. I was looking at the schedule and I am charted to get done with the very last section in the book today. So I'll be doing 4.2 and 4.7. The homework that's associated with these lessons I've been giving, the last of it is due on this Sunday, you know, the usual time, midnight. That means we're headed into the final. Next week we'll be reviewing for the final. And then I believe your actual final exam opens up, if I'm not mistaken, I think it says on the schedule that it opens up the 7th and the 8th. And that cannot be taken in any other window time other than that because the grades are due the next morning. All your grades are in. Everything has been updated so that you have very realistic view of what your average is going into the final. The only things that I have not put zeros in are for the portfolios, just in case somebody decides to hand in some of the ones that they just didn't turn in. However, if you do make that decision, I can't have a horde of portfolios coming in at the last minute because I wouldn't have time to grade them. What I'll be concentrating on in those last few days is doing averages, and that takes a lot of work so that I can meet my deadline for when they are due at the college. So if you are going to hand in any kind of late portfolios or fix any of the portfolios that you did not get maximum points on, no later than, let's see, what's the day before you, let's see, you're coming back. Let me check out the calendar real quick. You're going on Thanksgiving break. So your last day of school. Okay, yeah, so the last day that you can turn them in, anything that's going to be late, which is only the portfolios, because I can't get into the assignments once the due date passes. So the last day, if you're going to hand in a late portfolio, is Wednesday, last day before we go on Thanksgiving break, and that's the 25th of November. Does anybody have any questions for me before I go on and finish this material? Okay, I have office hours after we get finished here all the way till 1:45. So if you need to discuss anything with me, you need help with the material, I'll be there for hours. The portfolios are finished, though. I'm sure you saw my announcement that I sent out. I always send out announcements regarding how we're going to wrap this up. I'm going to remind you again that the last exam, the final exam, counts for a little bit more than just a regular test, and it's going to be administered only through Honor Lock. You will not be able to get into the final exam unless you've downloaded the Honor Lock software. So next week, I'll be sending out directions regarding how to download the HonorLock software. And again, as I stated last time, I brought this up during one of my lectures. You're going to ask to present a photo ID. They're going to take a 360-degree view of your room, meaning you'll have to get up and show all aspects of the room at various times at the beginning, and then they usually ask you during the test to do it once or twice. You're going to have to show a clear view of your workspace, meaning you need just a table with nothing else on it. Can't have your cell phone out, obviously. You know, they try to make it as secure as possible. You can only have one piece of scrap paper, I think, out at a time. I will let them know that you can have 4 note cards, one for Unit 1, Unit 2, Unit 3, and the few sections that we've done in Unit 4. So I'll let them know that you can have 4 cards. The size can be no bigger than 3 by 5. So those are, you know, small standard index cards. And you can fill out the front and the back with whatever formulas you want. As we review, as you do the review next week, every time you do a problem, if you unless you have saved your cards, that would have been great if you did save your cards from each test, and you can just use those, but you could add to them if you need to, or you can make them over, whatever it is that you want to do. So let's wrap up this little last bit of material, 4.2 and 4.7. Last time we got together, we were talking about inductive and deductive reasoning. Let me switch over to my document camera. Okay, so we began by talking about inductive reasoning and did quite a few examples having to do with inductive reasoning. And that the inductive reasoning, the main thing about inductive reasoning is that a person is reaching a conclusion, better known as a conjecture. That's what a conclusion, the conclusion that you reach when you're using inductive reasoning is called a conjecture. But that conclusion that you reach is based on just isolated instances that you have observed of a certain condition. And so you just come up with this assumption based on what you've seen. So that is the kind of conclusion, a conjecture, that can be disproven. It can be proven false by simply coming up with what's called a counterexample, an example that goes against what you have just claimed as your conclusion, or what's called as a conjecture. So inductive reasoning is not considered a fact, whereas deductive reasoning, when you are coming to your conclusion, you are using nothing but things that are known to be true, statements that are known to be true. Those are called rules or principles. And you use those things to reach your final conclusion. Therefore, since every building block that has gone into your conclusion is true, your final conclusion has to be true. In deductive reasoning, the conclusion is actually called a conclusion, and it cannot be proven false, as it can be in inductive reasoning. Those are the main differences. We did quite a few examples, lasted the whole period. So now, that's just a little summary of what we were doing the other day. We're moving to section 4.2. And in fact, I had demonstrated this when I was doing a problem having to do with inductive reasoning, and there was some kind of problem in the book, because I did quite a few problems from the book. And it was about right triangles, and they were trying to say that every right triangle was isosceles, that every right triangle in the world had the 2 legs equal, and that wasn't true. So I went into the Pythagorean Theorem on that problem in an effort to provide a counterexample and prove that that wasn't true. Hold on for 1 second. We got dogs gone mad over here. Sorry. Okay, so anyway, like I said, I had brought up this Pythagorean theorem, and I'm going to reinforce it with a couple more examples here. Pythagorean theorem, I'm sure you've seen this before because it's actually used at all levels, pretty much all levels of mathematics. Once you learn how to square a number, once you get to that level and take a square root, so probably from middle school on. It has to do with the sides of a triangle, and you know that this slanted side, which is always the longest side, and it is always the piece or the side that's across, right across from the right angle. They will be right across from each other. These two sides that come together to touch at the right angle or intersect at the right angle, these are called legs. So this is a leg, this is a leg, and this is the hypotenuse. So you have to remember that whenever you're writing the Pythagorean theorem, some books like to use letters like this. I prefer to write it out in words. So I will write what has been written here, but using words, because for me, it's easier to memorize that way instead of just an arbitrary A, B, and C. Because sometimes you get to a right triangle and they haven't labeled the sides with A, B, and C. Sometimes they've labeled it with other kinds of variables, and then I feel like students get confused. So it's always hypotenuse squared. The hypotenuse must always be kept on one side of the equation all by itself, but the legs are kept on the same side. So this, if I write it out the way I usually write it out, it would be legs squared plus other legs squared. And that's the Pythagorean theorem. You can write it like that in letters, or you can write it like that. Okay, just remember, and you can keep whichever side you're putting the hypotenuse on, again, it needs to be by itself, and it can either be on the right side or the left side, it doesn't matter. I usually start off by mentioning the hypotenuse. So if I was going to do this following problem here, anything that has a formula, I write the formula first. I cannot stress that enough that helps you get focused, and it helps you start organizing your thoughts about where you're going to plop each number. So here's my theorem that I'm planning on using. Hypotenuse squared is equal to legs squared plus legs squared. And then let's just reinforce here for you that right across from the right angle, the square represents the 90-degree angle, is always the hypotenuse. And then the other two pieces are called legs, so that you can very easily know what to plug in where in this equation. So the hypotenuse would be the x. This formula says square everything. So we're squaring that hypotenuse. One of the legs is 40, other leg is 9. Okay, then you get your calculator to assist, or if you know these numbers, then go for it. If you put 40 squared in your calculator, you're going to get 1600. And if you put 9 squared in your calculator, you're going to get 81. Okay, and just to demonstrate that would be 40. Push a little square button, bing, there's the 40 squared. And then, of course, 9 squared, and most people have that memorized, is 81. And then whenever you're doing the Pythagorean theorem, let me mention that the last thing you're going to do, last step, is always going to be taking the square root. So try not to do that too soon. Don't jump the gun and start trying to take the square root in the middle of the problem. We are still in the middle of the problem. That is because there are still things that I can do to simplify this, such as putting these two numbers together. So 1600 plus 81, 1681. Now I'm ready to take the square root. When you see that there are no other numbers on the side where the squared term is, there's no multiplier in front of it, no coefficient, then you're ready to take the square root, and not until you've gotten all these numbers together. So you know that we've been learning how to solve equations. And the main theme for solving an equation is that you isolate the variable. You want to try and get any numbers whatsoever that are on the same side with the variable, you want to get rid of them. Move them to the other side, get rid of them. You can look at it either way, and you accomplish that by performing inverse operations. That's the same thing as saying opposite operations. So here is a number on the same side of the variable. I want it to go away. The operation that this represents is squaring. This says x squared. And the inverse operation for squaring, or what we call the opposite operation, inverse is the mathematical name, opposite of squaring is square root. Also remember that when solving equations, whatever you do to one side, you must also do to the other side. So we are getting rid of the square by taking the square root of x squared and out pop the x. And then you can refer to your calculator, get it to help you with square root of 1681. And I mean, you can put the parentheses there. It's going to give you the answer either way, whether you close it or not. What I do want to stress is that when you put a number inside of a square root and it comes out a perfect integer like this with no decimal portion, that means that this number is what is called a perfect square. In other words, it can be broken down into the square of two numbers. That number would be 41, which is why 41 is a square root. That means that this number can be broken down into exactly 41 times 41. Because you know, another way to look at a square root when you're learning to do them by hand rather than with a calculator, they tell you that you need to break this number down into two factors, something times itself that equals this. And any number that repeats twice identically underneath the square root is the square root. That number would be 41. However, sometimes the number is not a perfect square. That's when you're going to get a decimal, and that's when the problem will say round to the nearest tenth or the nearest hundredth or whatever they feel like asking you to round to. So some of the problems will come out like that. Okay. Let's see, moving to the next one, we have more of a picture-based type problem and a description of the scenario above it. So it says the length of a shadow, you know, when you're walking on the sidewalk, your shadow usually stretches out in front of you. So in this case, the building is casting a shadow. So this is the shadow right here. Here's the building. It is casting a shadow, and that's because the sun is slightly behind it, above it and behind it, which will cause an object to cast a shadow. So the shadow, as they describe in the wording above this picture, is on the ground. This is the hypotenuse. And then it says the length of the shadow is 31. We got that. The distance from the top of the building to the tip of the shadow is 37. So they place that right there. Find the height of the building. So we do not know what the height of the building is. We'll just call it H. Okay, so what do we have? Nothing more than what we did here. It's not twisted in the same manner, but it doesn't need to be. You just need to know that across from your right angle, the side that's across from your right angle is called the hypotenuse. And you can call this X if you think calling it H is going to get you confused. You can call the unknown anything you want. We do not know how tall this building is. And really, these numbers that we're trying to discover are just part of a right triangle where the 37 is the hypotenuse. This shadow, it's a leg. And the height that we're looking for is also a leg. So we write down the theorem that goes with all right triangles concerning the sides anyway. And then we put in the hypotenuse here. Hypotenuse always gets kept by itself. And as I said, hypotenuse, the piece that's by itself, can either be on the left or the right, either one. And then the legs are 37. Does not matter which of the legs you write first. You're going to get the same answer either way. Okay, those are my two legs. Whoops, let's see, what did I do? I did that wrong. So that is supposed to be, sorry about that. Popped that 37 in the wrong place. So the 37 is the hypotenuse right there. And then one of the legs is called x, and the other leg is called 31. Okay, now you can get your calculator to help out. Okay, so let's see, 37, and we're going to square that. And I get 1369. And over here we have x squared, and we also need to know what 31 squared is, which is 961. Now the problem that I'm doing here happens to have one extra step when you compare it to the problem that I just did, and this is why. So this would be considered level 2 of the Pythagorean theorem, where you actually have to move things from side to side and take the square root. We didn't have to do that here. The reason was that in this problem, see how the variable that we were solving for was already by itself? There were no other numbers added or subtracted to that x squared term. So it didn't have the extra step that this problem is going to have. So all we had to do was square and square, like we just did. We just squared two numbers. We did the same thing here, but in this problem, they happen to be on the same side. So we can just combine them and take the square root. On this side, in this problem, that's not the case. Your x squared has a number that's being added to it, and you can't take the square root until you get this by itself. So to make this 961 get out, cancel on this side, but end up over here, we have to do the inverse operation. So opposite of addition is subtraction. You could also look at that as a negative 961 and then mimic that move over here. Okay, so now we have just x squared on the right-hand side, and you can get the calculator and figure out 1369 minus 961. That turns out to be 408. And then notice that in this problem, they're actually asking you to round to the nearest tenth. That means that the square root that you're about to get is not a perfect square. It's actually going to be in decimal form because it's not a perfect square. So that's why you're going to round. So we want to get rid of the square. Taking a square root is what undoes the square. It makes it cancel. So that's going to be gone. Out pops the x. Since we took a square root here, we're going to also take a square root there. So second square, 408. And they asked us to round to the tenths place, so that would be 20.2. Okay, and that's a couple of examples of Pythagorean theorem. Also in section 4.2, this came up previously. There must have been a problem or two, or maybe this student was just ahead. I remember somebody in the lecture asking me if I could give an example of the distance formula. Well, it formally gets introduced in this section, and all it says is that when you have 2 points that are on a slant like this and you want to find out what's the distance from here to here, you need to use this formula. I mean, if the points were like this, let's say you had 2 points that were like this, and I said, hey, find the distance between these 2 points, you don't need the formula, because you could, when they're straight across like that, horizontally arranged, you can just count up how many spaces there are. 1, 2, 3, 4, 5, 6. The distance is 6 from there to there. Or if you have points that are arranged vertically, you could also get away with just doing the distance by counting without using this big long formula. Just be 1, 2, 3, 4. Okay, that would be your distance here. This would be the distance here. But when they're on a slant like this, you have to use distance formula. So we're going to do that for these 2 points. Okay, I would suggest that any formula, just like when I introduced the slope formula that had a minus on the top and a minus on the bottom, anything that has minuses in the formula, it causes the sign of the number that you're going to plug in after the minus sign, it causes it to switch. And a lot of students get that mixed up. They think that if they're putting in a negative number, that that's the negative in the formula, and it's not. These cause a lot of times double negatives to occur. So I will put those in first. It cuts down on a lot of mistakes. So in this particular problem, I would arrange the whole square root. I would put a parenthesis where I'm going to put my x's and make sure to put that minus in. There's a plus in the middle. And then I would put a parenthesis for where I'm going to put my y's and go ahead and put that minus in. Now, when you go to put these numbers in, you can either move in this direction if you'd like, or you can move in this direction. That's up to you. But once you make that decision on which way you're going to move, from here to here or from here to here, when you do your x's, then you have to stick to it for when you do your y's, or that will make the answer come out wrong. But initially, it is your choice which way you want to move. Because a lot of students think that this means, hey, I have to start with the second x value, the one that's over here. That is not what that means. X2 and X1 just means that you have two different x values. So they gave one the name x sub 2, and they gave the other one the name x sub 1. I'm going to move this way. So my x's are 7 and 7. Most of the time they don't match, so I don't know if this is the greatest example, but we're going to do another one down below anyway. And then since I moved this way when I picked up my x's, I'm going to move this way again. Remember, consistency when I do my y's. My y's are -7 and -3. -7, -3. I would pay attention to those double negatives, rewriting them like this should be rewritten before you put it in your calculator, if you're even going to put it in your calculator. That has a square on it. This is just 0 squared. So 0 squared is just 0 times 0, so that's 0. This, on the other hand, is -4, and let's also talk about that. All of this still happening underneath the square root. Squaring, number one, never results in a negative. You can't, it's impossible to get a negative when you're squaring something, because squaring means to take that number and multiply it by itself. So -4 squared means -4 times itself. So even if the number starts out negative, you're still getting a positive. The reason students many times mess this up is because they resort to their calculator for everything, and then on top of it, they don't really know how to enter it. And students continue to have that problem through a lot of the classes. So if you are entering something like this -4 squared, it must be entered with a parenthesis, because that tells your calculator, drag the negative with the 4 as you square it. You're telling your calculator to do that by putting in parentheses. You see, if you enter it like this, without the parentheses, you get a -16, and it's impossible to get a negative when you square it. It's because you didn't command it. What you're telling your calculator to do by entering it like this is you're saying, square the 4 and then throw a negative in front of it. But when you put it in like this, you're telling it, take the entire 4 with the negative and multiply it by itself. See the difference? One comes out positive, and that's the way it should come out to be. All right, so you had 0 plus 16 underneath the square root, or just 16. 0 plus 16 is 16. Square root of 16 is 4. That means that the distance from this point to this point, if you were to plot them, would be 4 units. Okay, one more example of the distance formula. A lot of negatives in this one. And that's why I'm definitely suggesting that you get yourself all set up first. By the way, you did a really good job on showing work this time. Very good. There weren't people handing in 3 problems when everybody else was handing in 17 or 18 problems. I realize there's a few problems on the test that are just observational. I know which ones those are, but you can tell by what everybody else is turning in whether somebody else sticks out. So good job doing that this time. I'm sure you'll continue that on the final, especially that being that it is such a big grade. All right, don't forget to put these minuses in. Do that first so that we'll recognize when double negatives start happening. Again, I'm going to move this way. I just like to start on whatever's there and then move to the next point. So my x's would be -8 and -2. And then my y values would be 0 and -5. Okay, I'm going to clean this up before I actually start thinking about what these two combined are equal to. I'm going to rewrite it in a simpler form. That double negative is really a positive. Now I'll put them together. -8 plus 2 is -6. And if you want to go ahead and square it, remember squaring never results in a negative. It's always positive. So -6 times -6, or put it in your calculator, but you're going to have to remember the parentheses if you are. Or just remember it always comes out positive. Okay, here it's really 0 plus 5 squared, which is really just 5 squared, which is really just 25. Again, all of this is happening underneath the square root, but there's no need to keep drawing the square root every time. Okay, so then we don't actually take the square root until we have a single number. So this would be 61 underneath the square root. And notice that in this problem, they didn't say anything about rounding. This is not a perfect square. I know that if I put this in the calculator, I'm going to get a decimal. And if you put it in the calculator, you'll see that. But since they didn't say round to the nearest tenths place or hundredths place, that means you're not supposed to go as far as putting it in the calculator. So learn to pay attention to that. Rounding, when they mention the word round or estimate, that means you may give a rounded off decimal answer. But if they don't say that, leave it as is. Okay, so that can't be broken down any further. Otherwise, I would write what the square root is as a nice perfect integer. All right, let me stop here for a minute. I've done the distance formula and the Pythagorean theorem because they are related to each other. I mean, like I could plot these 2 points if I wanted to, and then connect them and turn it into a right triangle. So that's why those are always taught together. Does anybody have any questions on those concepts, distance formula or Pythagorean theorem? Okay. So we're going to go on to the last section. Yay. Last time we'll have like a little lecture. When we get together next week, we're going to be doing some reviews for the final exam, and you guys will be doing them. I'm going to be standing by assisting with any problem that you can't do, because that is a way, way, way better way of getting yourself ready for the final, because then you get away, you start coming into the realization of what you still can't do, or what you might be stuck on, or what you might be just misinformed about, or just didn't understand it. So we're going to be doing that next time, student-centered. You'll be at the center doing these problems, collaborating, and I'll be standing by to assist. Okay, so, and it's probably going to be in Socrative, so it'll be your last couple of activity grades. Okay, so here we're going to study, you've probably seen these before, this is called a parabola. And the reason that we're looking at it is because whenever you have an equation, such as this is just an example, anything where the x is squared, when you go to graph it, it gives a parabolic shape. So anything with a squared in it, like for instance, look, when I put this in my calculator, you don't have a graphing calculator, but maybe you do. So when I want to get a graph in my calculator, I just go to y is equal to, wait, I'm in a different number system here because I was using it with my trig class. So let me change the mode back to function. Okay, so now when I press y is equal to, and I can just like actually put that in there. But as I said, anything with a x squared is going to give you a parabolic shape. And when there's a positive in front of it, it's going to open up. And if there's a negative in front of it, it's going to open down. So like for instance, x squared plus 3. And if you graph that, there it is right there. And I can even change the window to give you a nicer view. See, just a basic parabola. The reason that it's up in the air at +3, that's called the y-intercept, because it cuts through the y-axis right at 3, is because of this +3. It takes the parabola that would usually be attached right at the origin and it lifts it up 3 units. That's what we call a vertical shift. Here's, a couple more examples. Let's say that I was going to give you let's say I gave you a negative in front of my x squared, and then, I don't know, -5. Let's say I give you something like that, so you can compare them. There's the other graph right there, the negative that I put in front of the x squared, that negative right there that the blinker is on, that's what flips it upside down when there's a negative coefficient in front of your x squared. That -5 that you see, it takes, again, the parabola that would have had its vertex, the turning point that is, it would have had its vertex at the origin, 0, 0, but instead it yanked it down 5 units. Again, there's the graph right there. Notice how this parabola, instead of being attached at the origin, has been yanked down 5 units. Okay, so just, just a little summary of what the parabolic shape is. Again, it is caused by the x being squared. When there's a positive number in front of the x, that means that the parabola will open upward like a bowl that you could fill cereal up with. And when there's a negative coefficient, it opens downward like an umbrella. Okay, so here we go, and those have to do with the questions that you see here. You're only asked some really basic things with regard to parabolas. First of all, does the parabola open upward or downward? But well, since they were nice enough to give you this picture, you can see very well that it opens like a bowl, opens upward, and that's because these legs shoot upward. Find the intercept. We need to remember from chapter 2 what an x and a y-intercept is. An x-intercept is where the graph touches or intersects the x-axis. Intersects means touches. Intersects the x-axis. So where does this touch the x-axis? At x equal to 2, which can be written like this. If you want, you can give the answer like this. You could say that this point right here is called 2, 0. All x-intercepts have the actual x-intercept in the x position and the y-coordinate being 0. Anything that's on the x-axis is like that. Y-intercept is where the graph intersects the y-axis. So when you look at this picture, you see that this graph intersects the y-axis at y equal to 1, right up there at y equal to 1. So you can write your answer like this, or you can write it like this. That point is called 0, 1. Okay, just like you could call this, you could call it x equal to 2, or you can call it 2, 0. Give it in point form or as an equation. Okay, let me kind of get this out of the way because I also want to introduce you to what's called the axis of symmetry. So parabolas are what we call symmetric. In other words, you could fold the paper. You could fold your paper that the parabola is drawn on right down the middle, and when you open it up, you would have matching images on either side of the creased paper. We call this the line of symmetry, the axis of symmetry, and it splits the parabola into 2 symmetric pieces, 2 mirror images, as they can be called. So there's a formula, a specific way that you give the axis of symmetry. It is actually an equation. See, find the equation of the axis of symmetry. So first of all, I want to tell you that, see how this parabola is decreasing? It's coming down, down, down all of a sudden and it gets to this point right here. And then right when it gets to this point, which we call the x-intercept, all of a sudden it changes from going down, being decreasing, to going up, increasing. The y values are now increasing. So that point where the behavior of the parabola changes, it changes from decreasing to increasing, that's also called the vertex. So yes, I did call this an x-intercept because the graph happened to hit the x-axis at 2, 0. But this point can also be called the vertex. So this served two purposes. That's not always the case, but because sometimes the vertex will be up in the air down here, as you saw when I demonstrated those parabolic shapes on my graphing calculator. So yes, this did serve as the x-intercept, but it is also called the vertex. The vertex is always the point at which it changes from decreasing to increasing. So when they say write the axis of symmetry, they want to know the name of the line that splits this graph right down the middle. See that on either side of this line that I have just drawn, you have symmetric images. Like you have all of this over here, and then you have a matching image on the other side. Everything over here. So if you were to crease your paper right there on this axis of symmetry, you would have matching images. So the way that you name the axis of symmetry is with this equation. X is equal to the h value. And let me tell you what the h value is with respect to parabolas. That vertex, again, we said that that vertex was called 2, 0. Let me get this out of the way just so we can concentrate on the numbers here. When you're talking about a vertex, this first value, I know that you call it x and y, but when we're talking about parabolas, and if you were going to study parabolas further, there are a lot of equations. How to put a parabola in standard form, how to put it in vertex form, different things like that. So we always refer to the vertex, that vertex right there, as h and k. The h is synonymous to the x value, and the k is synonymous to the y value. So this would be h, this would be k. All right, so when you're doing the axis of symmetry, you only use the h value. So when it says, give me the equation of the axis of symmetry, it's always x is equal to, because all vertical lines that run up and down like this are always named using the variable x, because every single point on this line has the same x value. That's why lines that are vertical are named using the variable x. Every single point on this line happens to have an x value of 2. So that is the name of the equation. Like if I was to name this point right here, that would be 2, 4. See? That point has an x value of 2. If I was to name this point right here, it's called 2, 6. If I was to name this point right here, it would be called 2, 10. So since every single point on this line, the one that splits it down the middle, has the same x value, this line is described as x equal to 2, all points that have an x value of 2. So this is what we call the axis of symmetry equation. You don't just give it as a number. You don't list it as a point. It's called x is equal to because it's a vertical line, and then the number that repeats for all points was 2. And it'll just be the front value of the vertex. When it said what is the coordinates of the vertex, I had already mentioned that to you because you kind of need to concentrate on what the front number in the vertex is just so you can answer this question. So I don't know if I can fit that in there. I'll just write it down here. That was 2, 0. Okay, let's see if there's anything else. Here is another parabola problem, only obviously this one opens downward. And if you did have the equation that went with it, that wasn't provided here, you would see that there would be a negative in front of the x squared. So when it says, does the parabola open upward or downward, you can see that it opens down. Find the equation of the axis of symmetry. Well, if you're going to find that equation, which will be x is equal to something, you need to concentrate on the vertex. That's this question down here. So why don't we do that first? Because that has everything to do with this equation for the axis of symmetry. All right, so this is my vertex right there. That is the point at which it changes from increasing to decreasing. Okay, so this point is, let's see, these lines are very light, but if you go all the way up, this line right here, you see that what I went through right there is an x value of 1. So this line right here is called x is equal to 1. But again, it's because of the vertex. Look at what the vertex is called. This point right here at the top, where the legs of the parabola switch from being increasing to decreasing, rising to falling, that is called the vertex. That vertex is named, let's see, this point is 1 unit over 9 units up in the air. These have names. Yes, they are called x and y, but when you're doing a study of parabolas, this takes on the name h, this takes on the name k. So basically whatever that x value is, that's what's going to go into your equation. X equal to 1 is the name of this line. Again, all vertical lines, when you name them as x is equal to some repeating number. Again, notice that anything on this line, this axis of symmetry, I'll abbreviate it like that. Anything on this axis of symmetry has an x value of 1. Like for instance, if I was to name that point right there, that is 1 unit over and 2 units in the air. If I was to name this point, it would be 1 unit over, 6 in the air. If I was to name something down here, this would be 1 unit over this point, -5. So everything on this line has an x value 1, and therefore that dictates the name of this line, which represents the line that splits the parabola into 2 symmetrical halves. And that's called the axis of symmetry. Okay, so the vertex is 1, 9. That's that point at the top. This is the equation for the axis of symmetry. Remember, it has to be in equation form, and it will start with x. The x-intercepts, I had reviewed with you that that's where the graph touches the x-axis. This time, there happens to be 2 of them, because depending on where the vertex is, if it's not right on the x-axis, then you're going to have both of the legs cutting right through the x-axis. So therefore, the graph cuts right into the x-axis right there at, let's see, that appears to be 2, 3, 4, 4, 0. So that's one of your x-intercepts if you're going to give it as a point. The other place that this graph cuts into the x-axis is right there, which is at -2. So this is an x-intercept. This is an x-intercept. Okay, so you can say the x-intercept like this, the one that's at 4, or you can say it like this. At x equal to 4, the graph cuts right through the x-axis. You can say the other x-intercept like this, or this. Okay, then with respect to the y-intercepts, that's where the graph touches the y-axis. This graph cuts right through the y-axis at 8. That point is called, oops, ran into a stapler. Move this over. Okay, so that point's called 0, 8. It's 0 units to the right or to the left, but 8 units up in the air. So that's called your y-intercept. Whoops, let me float that down. So the y-intercept is, you can call it 0, 8, or you can say at y equal to 8, the graph cuts through the y-axis. Okay, very last concept that you will be responsible for in ALEX and on the final is knowing how to evaluate. This has already happened in a couple of the other sections, but this time they're writing the equations in what's called function form. That means they have named this equation using what we call function notation. This is function notation. And here's what I'll try to explain to you what it means. This is the name of the function. They can use lowercase letters or capital letters. So this is called function f. And this little notice that you see right here where there's an x in parentheses, it means the function f is written in terms of x. That means you will see the rule that represents function f. You'll see it over here, and you'll see nothing but x's in that algebraic rule. This is called the function rule. You're going to go by this rule to get any values that represent the f function. This is called the g function. It is also written in terms of x. So in other words, when you come over here to look at the rule that describes the g function, you see nothing but x's. So we say that it is written in terms of x. So when you see a notation like this, this just means go grab the rule that represents the f function and plug in -1. Remember, the rule is the expression on the right side of the equation. So they are asking you to go grab the rule for f, the function called f, and to plug in -1. So we're going to go 3x cubed plus 5. And what we're going to be plugging in is what they've told us to plug in right here, which is -1. Now you can put that in your calculator if you'd like, and I'll demonstrate that. Plus 5. Okay, so it would just be 3, open up a parenthesis, plop the -1 in there, close it up, and raise it to the third power. This is you can use this as a power key. Right under the clear button, there's a caret key. And then you are adding 5. So just like you see it on the paper. 3 times -1 cubed plus 5, press enter, the answer is 2. And if you want to, you can write the answer like this. When I took the f function, the rule that is, and plugged in -1, the answer was equal to 2. You can write it like that. You can even write it as a point. The number that you plugged in represents what you plugged in for x, therefore it is the x value. And the answer that you get represents the y value. So for this one, we're doing the same thing, only this time we are being told to go grab the function called g, and we're being told to use the rule that's over here on the right that represents g, but plug in a -3. That is the command that's being made here. So we go grab the rule, but of course we leave a blank spot wherever the x's are, because otherwise how could you plug in this number that they're trying to get you to plug in? And then you put in the -3, and we go for an answer. That would be -15. Of course, you can put it in your calculator if you'd like. That times that is -15 minus 1 would be -16. And again, there are various ways to write the answer. You could say the g function, when -3 was plugged in, resulted in an answer of -16. Or you can write it as a point. -3 is what I plugged in for x. -16, the answer, represents y. Okay, any questions on that? Okay, so hold on for 1 second. We're going to do our Socrative activity that has to do with, there's no questions for 4.7 on there, but there's questions for 4.1 and 4.2 for you to review, because I created this yesterday. So hold on for 1 second. Let me get into Socrative and open it up. Okay, I'll be standing by to take your questions. Let's see, just, type in or just say it out loud if you do have a question that you want to ask. I don't think I'm going to put you in groups. I don't have enough time for that. So go ahead, go to Socrative.com. Remember, the name of the classroom is always my last name, Zeiss, and I will type that into the chat box. Feel free to ask questions if you need to.